For a land-loving species like ourselves, the seas are lovely, dark, and deep. Unplumbed, and often better left that way. But take a giant step back, and it's clear the oceans define our planet. Land masses become afterthoughts, commas and parentheses in a much greater story. And the seas have a way of reminding us now and again who's really in charge. They inundate, they tower and smash, they shrug mightily and create tsunamis. They exhale and spin off super hurricanes. And beneath the bounding main, they hide wonders. Phantasmagorical seascapes smoking and growing. Islands in the making. Creatures beautiful and utterly strange. Plunge into the ocean depths and examine their hidden riches. Step back in time to find out how it all began and how we got to today. And come to understand what this relentless force of nature can do at its most violent and most beautiful on our amazing planet. Water. A single drop of it is a miracle. Colorless, tasteless, odorless. It is part of every living thing on the planet. And it has been here since almost the beginning of the Earth. It has been belched out of volcanoes as vapor, risen to great heights, fallen back to Earth as rain, fed life, returned to the soil, to rivers, and to the sea, perhaps to be sucked down into the molten Earth again. A journey that each molecule in this drop may have taken thousands of times over millions of years. In it, life teems. And that's just a drop in the bucket. And what a bucket. No other planet in our solar system can lay claim to this strange blue liquid that made life possible and can also destroy it. More than 70% of the surface of the planet is covered with water. And that's just the surface. In volume, water fills up 320 million cubic miles. Some 95% of the livable habitats on Earth are in the oceans. If we were to divvy the oceans up, each person on the planet would have more than 50 billion gallons of water apiece. 5 different oceans dominate the globe. The Arctic, Atlantic, the Indian, Antarctic, and the stupendous Pacific, mother of all oceans. All of these bodies of water are so profoundly connected to each other that most oceanographers refer to the world ocean, a single marvelously complex entity. It is tossed by winds, tugged by the moon, driven by an invisible conveyor belt, and warmed by the sun. It can never rest. It is made of a substance so amorphous, it can take the form of a solid, liquid, or gas. To make matters more dizzyingly complex, the ocean's influence reaches high into the atmosphere. Each day, they absorb enough of the sun's energy to feed the world's oil demands 3 times over, the equivalent of 250 billion barrels of oil. Each day, 1 trillion tons of water evaporate, taking millions of megawatts of potential energy into the atmosphere. The results are titanic. This ocean-atmosphere dynamic is the hydrosphere, the water world. It was long assumed that the ocean floors were as blank and featureless as the ocean surface itself. But their topography is even more complex and varied than that on dry land, with mountain ranges longer and taller than the Himalayas and trenches deeper than the Grand Canyon. Our tour begins with the continental shelves, just beyond where you stick your toes in, submerged, gently sloping parts of the continents themselves. In the tropics, starting just yards offshore, we find the unequaled splendor of the coral reefs, a brilliant intermarriage of geology and biology. There are over 125,000 square miles of coral reefs across the globe, mostly in the tropics. The corals themselves are living things, but live on and among the limestone skeletons of their dead predecessors. They are architects of some of the largest skeletal formations in the world, providing natural breakwaters that protect shorelines. The largest of these is the Great Barrier Reef off the coast of Australia. The Great Barrier Reef started forming over 3 million years ago, when sea levels were far lower than today. As sea levels gradually rose, the corals kept pace, growing upward toward the sunlight. They now reach nearly 200 feet high. And their structure slows down the powerful wave energy of the open ocean, providing a stable environment for marine life to thrive over millennia. The coral reefs are home to an astounding number of interdependent species. It's a teeming Eden, a fantastically gaudy tranquility, punctuated by violence. In such a crowded coral reef community, symbiosis is a way of life. This fish, the parrotfish, does the reef an interesting favor. With powerful jaws and beaks that crush hard coral to extract the algae within, they grind the coral's skeleton and they defecate the crushed sediment over the reefs. Thus, the parrotfish manufacture much of the sand in the coral reef community. Sand that filters sediment from the waters and protects coral from coastal erosion. The web of life on the ocean's reef is bustling, dense, and complex. Some attach themselves to the coral itself. Others cling to it, and with chameleon-like skill, hide in plain sight from predator and prey. Still others seek safe refuge in its crevices and venture out at night to hunt and feed. But not all these fish live in the reef. Many merely swim by for takeout. Part-time visitors to the reef, sharks, skates, rays, and countless others. Beyond the reef, further along the continental shelf, we drop deeper and deeper into the ocean. The continental shelf continues to slant gently away to a depth of about 650 feet. Next, we reach the continental slope, which can plunge down over 5,000 feet to the deepest parts of the ocean. Beyond the continental slope is deep ocean floor, the abyssal plain. For long stretches, it is as flat and featureless as we once thought the seafloor would be. But in places, it is punctuated by some of the most fantastic canyons, mountain ranges, trenches, and volcanoes on Earth. And nothing is quite as spectacular as the mid-ocean ridge, the largest geological feature on the planet. It runs 40,000 miles across the world oceans. These are the seams where the world is tearing itself apart and creating itself anew, spewing lava and heating up the crust. Along the ridge are hydrothermal vents, chimneys, and black smokers. This is where water and gases heated by the inner Earth force their way out. Ocean waters are sucked into the crust and spit back out with a different chemical composition. It's a fine-tuned machine, albeit a slow one. It may take millions of years for all the water on the planet to cycle through these vents. They act as filters do in a fish tank, cleaning out and rejuvenating the ocean's waters. The water from these vents is heated by molten magma beneath the Earth's crust. The crust, after all, is merely a thin film surrounding an enormous ball of molten energy. The magma-heated water is constantly escaping where it can, creating these fantastic chimneys and smokers. And they create one of the most extreme environments in the world. Far beyond the reach of sunlight, at depths of 7,000 feet, with extreme pressures and temperatures beyond 700 degrees Fahrenheit, it's the last place you'd expect to find living things. Or is it? Oddly, a resilient community of surreal organisms calls this place home. And they manage to survive completely cut off from what happens on the surface of the planet. Without any sunlight, they live off chemical compounds from within the Earth that we humans find toxic. Here, where the Earth is giving birth to itself, we find a clue as to how life itself may have been born under the brutal conditions of the primordial oceans. But that begs a question. Where on Earth did the oceans come from in the first place? In the beginning, Earth gave no clue that it would one day become that big blue marble in the sky. When it began to coalesce some 4.6 billion years ago, the planet was a super-hot, molten sphere. Racked by super collisions as its gravity reeled in, and the primordial planet reeled from, a bombardment of asteroids and comets. Sometime in the first 200 million years, the bombardment slowed, and cooling took hold long enough to give the Earth a thin black skin. But the Earth was still so hot, the skin kept swallowing and recycling itself back into the molten mantle. Nothing like a continent could form yet. Giant cannonballs of lighter magma were shooting to the Earth's surface from deep within its mantle. Eventually, the cooled, hardened magma reached the surface and refused to be subsumed again. Finally, the first continents could begin to form. The Earth was about to undergo a sea change. All along, the Earth had been belching out gases from its molten magma. Water vapor began saturating the atmosphere. When the saturated atmosphere could hold it no longer, water vapor droplets formed, and the skies opened. Eventually, the hot Earth found itself deluged by a torrential downpour, lasting perhaps millions of years. Nascent oceans formed, but it seems continuing asteroid and comet bombardments may have evaporated them, rocking the Earth and starting the process all over again. Finally, 3.8 billion years ago, the Earth emerged as an ocean planet. But these were not like the oceans we have today. The early oceans were acidic, dense, shallow, and corrosive. The skies above glowed red from particles in the atmosphere, and somehow there was life. These are fossils of extremely primitive bacteria, almost 4 billion years old, that may have lived in ancient steaming mud pools, much as heat-loving organisms have been found thriving in the harsh wet heat of geysers and hot springs today. Where life may first have taken hold around the underwater volcanic vents like those found on the mid-Atlantic ridge. By about 3.5 billion years ago, despite hot lava still spilling forth above and below the oceans, strange domes and pillows of a new kind of life had taken shape in shallow water. Their descendants to this day can be found in places like Shark Bay, Australia. These are stromatolites, colonies of bacteria. A kind of bacteria that can turn sunlight into food and burp out oxygen as a byproduct. The first photosynthetic creatures. As their numbers increased, they pumped more and more oxygen into the world. At first, the new oxygen stayed on the surface, absorbed by iron-laden rocks and water. But eventually, the concentrations reached the point where the oxygen had nowhere to go but up, into the atmosphere. At the time, oxygen was poisonous to just about everything alive, and it displaced the methane that kept the skies above warm. Thanks to the billions of tiny exhalations of the cyanobacteria over millions of years, the sky took on, for the first time, its blue tint. Ultimately, the stage was set for oxygen-dependent life to really take off. But something went terribly wrong. Apparently, the Earth turned into a cosmic snowball. Now, this is currently only a theory, but there's evidence from around the world that ice may have existed at the equator as well as the poles some 2.2 billion years ago. This is what some scientists think happened. All that oxygen destabilized the world climate by destroying the greenhouse gas, methane. And because oxygen isn't nearly as efficient at trapping heat as methane is, the world cooled dramatically. As snow and ice began to cover more and more of the cooling planet, it reflected more and more of the sun's energy back into space, leading to further cooling, leading to further ice, further reflection, and an even colder Earth. This chilly feedback loop is called runaway albedo. And believe me, you don't want to be around the next time it happens. Over millions of years, sea ice slowly groaned and cracked its way toward the Earth's equator. When it reached the tropics, it rapidly engulfed the tropical seas, and soon the entire globe was covered in ice. The frozen planet must have looked like something out of a science fiction movie, or perhaps a bit like Europa, Jupiter's frozen moon. When the process was complete, the surface of the planet was one big shimmering snowball, or something, a slush ball. Some scientists theorize that the entire Earth's oceans were frozen to a depth of half a mile below sea level. This begs two giant questions. What on Earth could survive such an event? And what else on Earth could have stopped the snowballing snowball? The answer may well be one and the same. Magma. Bless its hot red heart. It continued to spew out not only heat from the Earth's core, but greenhouse gases that could trap the heat from the sun. And it may well have provided warmer oases where life could hibernate long enough to survive the big chill. While the snowball theory continues to raise questions about the extent of Earth's deep freeze, few debate that it was Earth's inner engine of heat and lava that snapped it out of its cold spell. And by that point in Earth's history, that engine had already begun to do something remarkable to the planet's surface. Continents wholly unrecognizable today had surfaced and started to move, tearing apart, banging into each other, grinding by one another. The remarkable story of plate tectonics had begun, and in the oceans, life would never be the same. Jostled by the bumper car antics of restless continents, the story of Earth's oceans was about to get dramatically more dynamic. By 2 billion years ago, our Earth had begun to look vaguely familiar. There were continents, clearing skies, and endless oceans, chock full of bacteria. Perhaps 1 billion years ago, multicellular life emerged. Colonies of algae and later seaweed. At about the same time, the first supercontinent, Rodinia, appeared and broke apart again. What followed is a global billiard game of continents banging into one another, sticking together, breaking apart. By about 600 million years ago, the supercontinent Pannotia came together and broke up. In the ocean world around it, sponges, jellyfish, and flatworms prowled the seas. At about this time, another cataclysmic snowball apparently swept over the planet, jump-starting evolution once again. By 540 million years ago, the continents were flooded by shallow seas, and the amazing monsters of what's called the Cambrian explosion appeared in the oceans. Here the arms race of predator and prey really took off. Creatures developed hard shells and used pinchers as weapons. 500 million years ago, the continents surrounded the ancient Iapetus Sea. And an extensive inland sea inundated most of the ancestral North American continent. The first vertebrates soon appeared. Jawless fish resembling today's lampreys. Around 450 million years ago, the Panthalassa Ocean covered much of the northern hemisphere as the Iapetus Sea closed. And finally, came the kings of the oceans, sharks. It would take them 80 million years to perfect their killing ways. Then came their first golden age and millions of years of domination. By 400 million years ago, the continents had again crumpled together into a supercontinent, Pangaea, surrounded by the superocean, Panthalassa, and the much smaller Tethys Ocean. Sea levels fell substantially as ice covered much of the southern hemisphere and swamps formed along the equator. These waters eventually became the hunting grounds of ichthyosaurs and plesiosaurs, reptilian sea monster equivalents of the dinosaurs evolving on dry land. By about 225 million years ago, Pangaea began to break up, and slowly our recognizable Earth began to take shape. The infant Atlantic Ocean began to grow. What on earth could have been driving this bumper car game of crashing continents? The Earth actually is not solid. It's broken up into a dozen or so major plates. These float along the top of the molten mantle. Some move apart, some crash together, some grate by each other. As the plates shift, they change the shape of our oceans. At the mid-Atlantic ridge, two plates, the American and the Eurasian, pull away from each other at a rate of about an inch per year. Lightning speed in geological terms. Their movement is triggered by molten magma beneath the oceanic crust. On this ridge, the ocean floor is literally bursting apart at the seams. Superheated lava gurgles up, creating new ocean floor. But the magma doesn't need to seep through the crust to create beauty. Not far away, marine scientists have discovered something amazing. Fantastic geological sculptures. Spiral towers formed not by magma itself, but by the way it heats up the ocean floor. They call it the Lost City. Here we find mystical formations standing precipitously, nearly 20 stories off the ocean floor, like a wonderland of cathedral spires. Fueled by magma churning far below it, the crust has uplifted and split, exposing mantle rock. The spires tower from there. It has taken some 1.5 million years for this hot young crust to reach here from the mid-ocean ridge 9 miles away. But unlike the smokers at the ridge itself, these spires are not directly venting volcanic activity. Instead, they are built by a chemical reaction between seawater and rock, a reaction cranked up by the heat of the mantle rock. The pH here is like that of liquid Drano, but the temperatures hover around a balmy 170 degrees Fahrenheit. So what does the ever-widening Atlantic mean for the Pacific Ocean? It's shrinking at roughly the same rate. On the other side of the planet, just off the coast of the Marianas Islands, lies a volatile trench. At a depth of over 35,000 feet, the Mariana Trench boasts the deepest point on the planet. There's enough room here to fit 28 Empire State Buildings. It's nearly 7 miles down. But how did it get so low? The Mariana Trench is a subduction zone, the spot where the Pacific Plate and the Philippine Plate collide, where the Earth swallows the Pacific Plate into its belly. The subduction zones not only form deep trenches, they also trigger volcanic forces, and they wreak havoc on the ocean floor. The volcanic rim of the Mariana Trench yields more surprises. This is where the Earth pops the bubbling, at the deep ocean's champagne vent. Bubbles of carbon dioxide released from the crust percolate through the ocean to the surface, eventually reaching the atmosphere. How this CO2 affects our oceans is still anyone's guess. Around the corner and over the hill, we see sulfide chimneys standing 30 feet tall, where smoky hot gases are vented through the sea. Temperatures here are a cool 460 degrees Fahrenheit. Despite the boiling, toxic nature of the environment here, life has learned to live with it. Life that survives on energy from within the planet rubs shoulders with life that gets its energy from the sun, baffling scientists. Down the ridge, things get more violent. As the Earth heaves, the surface of the undulating crust cracks, giving way to molten lava. Violent eruptions spit fire and sulfur into the ocean. Primordial gases from within the Earth's mantle burst through the crust and are released perhaps for the first time in billions of years. And now that we've seen the marvelous engines that create such wonders, we look back to see how it has changed the planet as we know it today. $5 million years ago, a nanosecond in the scheme of things, and the Earth looks just as it does today. Right? Not quite. Look closely. There. North and South America aren't joined. A tiny little lost piece of the Earth's great big jigsaw puzzle is about to slide into place and change the world's oceans entirely. Not to mention the history of humanity. Nor the new pattern of violence about to appear in the skies above. It seems unimaginable that such a tiny change in our jigsaw Earth would utterly alter the course of the water world. Both the oceans below and the skies above. But it did. $12 million years ago, the ocean was in constant motion. Currents circulated, shifting, twisting, squeezing around the continents. North and South America were unconnected. Water moved unhindered between the Atlantic and Pacific along something called the Central American Seaway. And to the north, there was no Arctic ice. All of this was about to change. Farther south in the tropics, the Cocos Plate slid violently under the Caribbean Plate, and volcanic peaks broke the surface. Over time, sediments plugged up the gaps around the islands. And voila, the Isthmus of Panama was born. The isthmus cut off the free exchange between the Atlantic and Pacific. The direct line between the oceans was sealed. Nothing would ever be the same. With its passage to the Pacific blocked, any current running from the Atlantic had to do an about-face. Joining and turbocharging the early Gulf Stream, the currents turned up the heat in Europe. But perhaps the most profound change was in the far north. Some scientists think that the warm waters of the Gulf Stream carried more heat to the North Atlantic, causing more water to evaporate into the cold northern air. The evaporated water fell back into the Arctic Sea as rain and snow, diluting its salt levels. Fresher water, of course, freezes more easily. And by 3 million years ago, we had an Arctic ice cap. The white ice shield reflected the sun's heat back into space, ensuring its continued existence. Temperatures dropped further, and the ice cap became a key part of the powerful engine that drives the entire world ocean system, even today. It's called the Thermohaline Ocean Conveyor Belt. And it, more than anything, shows why the world's great seas are actually one great ocean. Here's how it works. When Arctic temperatures freeze the seawater, salt is locked out of the ice. The denser, saltier water pushes downward into the ocean and heads south. Currents on the conveyor take a global trip as they flow around the Horn of Africa, through the Indian Ocean, and eventually weave their way to the Pacific. The system curves around and repeats itself. The Gulf Stream in the Atlantic is so powerful, it transports about 40 million cubic yards of water every second. More importantly, this leg of the conveyor belt makes temperatures in the British Isles and Northern Europe much milder than they would be otherwise. That's why it's warm enough for palm trees to grow on the coast of England. The Because sea and air are so closely tied, the ocean conveyor affects weather profoundly. In some cases, with help from the rotation of the Earth, the ocean atmosphere dynamo works itself into a dangerous frenzy. The hot sun heats the sea surface, evaporating 1 trillion tons of water into the sky each day. The rotation of the Earth sends winds and ocean currents swirling over the globe. It's called the Coriolis effect. The momentum of the Earth's rotation deflects currents away from the equator toward the poles. They form a clockwise gyre in the northern hemisphere and a counterclockwise one in the southern hemisphere. Cold air currents clash with warm currents, creating storms. When ocean temperatures rise and storm winds pick up speed, vast amounts of water evaporate from the ocean's surface. Warm, moist air climbs rapidly upward and then condenses as it cools, releasing even more energy. Heavy rains fall and winds accelerate. Bands of thunderstorms begin to radiate outward for hundreds of miles. The winds crank up the storms as the oceans feed the rage. The force of the Earth's rotation, the Coriolis effect, causes the bands of storms to rotate into spirals, forming hurricanes in the Atlantic Ocean and typhoons in the Pacific Ocean. Hurricanes can stir up more than 1 million cubic miles of the Earth's atmosphere every second. With the onset of global warming, the seas have become the great repository of the extra heat. And it's beginning to look as though hotter oceans are feeding more and more monstrous hurricanes. Year after year, storms wreak havoc and destruction. And it seems in recent years, we have entered a period of heightened storm activity. As the sea temperatures continue to rise globally, so does the ferocity of the storms. But the water world may well have far more frightening things up its sleeve than hurricanes. As the continents have gone sliding and banging around the planet through the ages, congregating and then heading off in their own directions repeatedly, they have massively reshaped the oceans. But it's far more than shape that's at stake. All life is dependent on the water world, the way our oceans are yoked to our skies. Our oceans, despite their profound interconnectedness, have very different chemical makeups. Their own personalities, as it were. The Atlantic is saltier than the Pacific. The North Atlantic has the highest concentration of carbon dioxide, while the Antarctic has the lowest. The chemical composition of the oceans has changed drastically and abruptly throughout their history. Given that something as small as the Isthmus of Panama forever changed the way the water world functions, it seems clear that plate tectonics, creating new oceans here and slamming others shut there, has had a profound effect on the Earth as a whole. So what does the future hold? Thanks to plate tectonics, we can take a peek at what the planet might have in store for us. Could it be that in the middle of this hot, dry desert, an ocean is being born? The fault lines here in the Danakil Desert in Ethiopia are growing at a startling rate. With the Red Sea just over the ridgeline to the east, it is ripe for a deluge. A slight breach could send in the waters of the Red Sea, filling the basin of the East African Rift, creating a new sea. The momentum of the plates eventually slides Somalia and Madagascar out into the Indian Ocean. And Arabia pushes northward, eliminating the Persian Sea. All over the world, the movement of the plates begins to make our globe less recognizable. California seems intent on becoming an island, sliding north toward Alaska. Australia heads north, gobbling up islands along the way and becoming attached to Asia. Africa's huge mass drives northward toward Europe and eventually does away with the Mediterranean. The collision slowly thrust the Alps up to the heady heights of the Himalaya and beyond. How will all these continental antics millions of years from now affect the oceans? Well, it may not be pretty. We have grim evidence that the obliteration of a sea, like the Mediterranean, can have a huge impact on Earth. On the floor of the Mediterranean Sea lies a signpost of disaster. A geological feature tells the story of a different sea at a different time, dating back some 6 million years. It shows a small shoreline far below the waters of the current sea, pointing to a cataclysmic event that may have changed the course of human evolution. It was the Miocene epoch. Ancient mammals roamed the land. But around 6 million years ago, a continental collision crushed together the opening to the Mediterranean, choking it off from the Atlantic Ocean. With virtually no refreshment from the ocean and inadequate rains, over thousands of years the entire Mediterranean Sea evaporated, creating vast expanses of scorched earth. Elsewhere on Earth, even bigger changes were underway. For several million years, the Antarctic ice cap had been growing, turning more and more ocean into ice. The increased ice reflected more of the sun's energy back into space. An ice age resulted. The world's sea level dropped 165 feet, further cutting off the Mediterranean Sea from the Atlantic. Around the Mediterranean, entire species were wiped out and life decimated. Others fled. It was a cataclysm in the making. But then, the cavalry arrived. A very wet cavalry. Several 100,000 years after the Mediterranean evaporated, something caused the Atlantic to breach the Strait of Gibraltar. Nobody really knows what. The possible result was a giant 3,200-foot waterfall with a force thousands of times greater than Niagara Falls that shot through Gibraltar to fill almost 1 million square miles of the Mediterranean basin. If the ocean hadn't charged through the strait, we might have faced living on a frigid planet, if we survived at all. The Earth's climatic path could have changed, and the course of human history might be very different, or perhaps even non-existent. One theory says the Mediterranean crisis transformed woodland landscapes in Africa to open savannas, encouraging our early ancestors to descend from the trees and take a chance walking on 2 feet. We are here, it seems, by extraordinary chance. Who knows how many crises the Earth underwent during our evolution that could have changed us one way or another? And who's to say severe climate change won't happen again? Could a snowball deep freeze sweep across the world as we know it? Or could rising temperatures instead cause rising sea levels, creating a true water world? Let's look as far into future possibilities as our plate tectonics time machine will allow. We can see amazing changes, but not yet the force that almost certainly will drive all the continents back together, as it has done time and time again throughout the history of the Earth. In the next 50 million years, the Atlantic continues to grow, but its North American plate could begin to shrink. 150 million years in the future, the mid-Atlantic ridge may slide under North America, pushing the eastern coast of America high atop a mountain range, and the mighty Atlantic begins to disappear. By 250 million years into the future, the Pacific Ocean widens to encompass most of the globe. The continents compress into the future supercontinent, Pangaea Ultima. Imagine humanity on one continent. Will we still be here? Or will we have left already, taking with us the history of our blue planet as a story to be told again and again on different planets in different solar systems? One thing seems certain. Earth as home seems a place hard to forget. and we owe its perfection, its place as our home, to its oceans. For the time being, our oceans take care of us. And the engine that drives our planet's climate maintains a comfortable range of temperate zones and seasons across the globe. Our restless oceans always changing, constantly morphing. Will we end up in a snowball Earth, or one that's too hot to handle? And what is most likely to survive? Only time will tell, and either way, the oceans hold the key.